The moon is the most studied object in the sky. 12 people have walked on it. 6 missions have returned samples from it. More than 100 robotic spacecraft have orbited it, impacted it, landed on it, or flown past it. The Apollo program alone returned 382 kilograms of rock. The combined sample mass across all returning missions exceeds 400 kilograms. The combined orbital observation time across all missions exceeds 300 spacecraft years. By any reasonable standard, the moon should be the body in the solar system about which we know the most. It isn't. The moon is the body we have studied the most. Those are different statements, and the difference is the subject of this video. Each generation of measurement has revealed structure the previous generation did not see. Each generation has raised questions the previous generation could not pose. The moon in 2026 has more open mysteries than at any point in the history of lunar science, not because the science has failed, but because the science has progressed far enough to see what it does not yet understand. There are 7 of them. They are not equally deep, and they are not equally close to resolution, and I will say so as we go. Some will be settled by missions already in development. Some will outlast the careers of the people now working on them. All 7 are real, unresolved problems in the published literature, and all 7 matter for what the moon actually is. We start at the surface and work inward. For at least 400 years, observers have reported brief flashes, glows, and color changes on the lunar surface, events that should not occur on a body that is conventionally described as geologically dead. The reports are not fringe. The earliest catalogued observation is from 1540. The British astronomer William Herschel recorded several in the late 18th century. NASA, in 1968, compiled a list of 579 such observations spanning 4 centuries, prepared in support of the Apollo program because the agency wanted Apollo astronauts to know what to look for. Patrick Moore, the British astronomer who hosted the Sky at Night for over 50 years, catalogued his own observations across decades. The reports come from professional astronomers, from amateur astronomers using calibrated equipment, and from spacecraft instruments. The observations are real in the sense that they have been reported by qualified observers consistently for centuries. The question is what they are. 3 hypotheses compete in the literature. The first is outgassing, that the lunar interior, despite its slow cooling, continues to release small volumes of gas through the surface, and that the gas, when it reaches the near vacuum above the regolith, briefly illuminates as it scatters sunlight or as it disturbs the surface dust. The hypothesis has direct support. The Apollo 15 and 16 missions detected radon 222 emissions from specific lunar regions, and radon 222, with a half-life of 3.8 days, must be released recently, or it would have decayed before detection. The Lunar Prospector mission confirmed the radon emissions and mapped them to specific surface regions, including the crater Aristarchus, which is the single most frequently reported TLP site. The connection is suggestive. The regions that release radon are the regions where flashes are seen, but the connection has not been confirmed by direct observation of a TLP event coincident with a gas release. The second is impact flashes. That small meteoroids striking the lunar surface produce brief light emissions visible from Earth. This hypothesis is partially confirmed. The NASA Lunar Impact Monitoring Program, operating since 2005, has recorded several hundred impact flashes using small telescopes. The flashes are real, and the meteoroid origin is established. The problem is that the recorded impact flashes account for only a fraction of the historical TLP reports, and impact flashes cannot explain the reports involving sustained glows or color changes lasting minutes to hours. The third is observational artifact, that some unknown number of historical TLP reports reflect atmospheric distortion, instrumental error, or perceptual phenomena rather than actual lunar events. A 2005 statistical analysis by Krotz and Hummels found that TLP report frequency correlates with several observational variables: telescope quality, observer experience, observation conditions, in ways consistent with artifact contamination. The analysis does not eliminate the phenomenon. It establishes that some fraction of reports, possibly a large fraction, are artifacts, and that the residual real phenomenon is smaller than the historical record suggests. The current state of the literature is that all three mechanisms are probably real, and that no single one accounts for the full historical record. Some TLPs are impact flashes, some are atmospheric or instrumental artifacts. Some, the ones associated with radon emission regions like Aristarchus, are probably outgassing events. The residual category, the genuinely anomalous reports that none of the three hypotheses captures, is small, but is not zero. I rate this the least consequential of the 7 mysteries. Resolving it would tell us something about the lunar interior's residual activity, but the something would be incremental. The mystery survives on the list because it is the oldest unresolved question about the moon, and because the residual category, however small, is a reminder that the moon still produces observations the established framework cannot fully accommodate. It is also a reminder of a deeper question. If the lunar interior is still releasing gas, if radon is still escaping from specific surface regions after 4.5 billion years, then something in the moon's deep structure is still generating that gas, and something is still allowing it to reach the surface. The pathway implies an interior less inert than the textbook describes. And the interior, when we look at it through a different instrument, turns out to hide a more substantial mystery. The moon has a magnetic field. The moon should not have a magnetic field, and the contradiction has not been resolved. The moon as a whole has no global magnetic field. There is no dipole, no north and south magnetic geometry, no protective magnetosphere. The total global field, measured at any point above the surface, is approximately 1/10,000th of Earth's. The moon, in specific surface regions, has localized magnetic fields with strengths up to several hundred nanotesla. The localized fields are called magnetic anomalies. They are real. They have been mapped from orbit by multiple missions, and they have no agreed explanation. The first evidence came from the Apollo sub-satellites, which carried magnetometers into low lunar orbit in 1971 and 1972. The Lunar Prospector mission in 1998 mapped the anomalies at higher resolution. The Kaguya mission from JAXA in 2007 and 2008 mapped them at higher resolution still. The maps are now detailed enough to characterize the anomalies' spatial distribution, their depth structure, and their relationship to surface features. The distribution is peculiar. The largest anomalies cluster on the lunar far side, in regions geographically opposite, antipodal to the largest near-side impact basins. The Imbrium Basin on the near side corresponds to an anomaly cluster on the far side. The Serenitatis Basin corresponds to another. The pattern is too clean to be coincidence and is the principal clue to the anomaly's origin. Two hypotheses compete in the literature. The first is the ancient dynamo hypothesis, that the moon, in its first billion years, possessed a global magnetic field generated by a fluid core dynamo, that the field magnetized rocks at the surface as they cooled below the Curie temperature, and that the magnetization persists in the rocks today. The hypothesis predicts that the anomalies should be distributed in proportion to the surface rock's magnetic susceptibility, which depends on composition. The hypothesis has support from the Apollo samples. Several Apollo basalts, when measured in the laboratory, retain magnetization consistent with formation in a global field of substantial strength, in some cases comparable to Earth's current surface field. The hypothesis is widely accepted in its basic outline. The problem is the antipodal pattern. The ancient dynamo hypothesis predicts that magnetic anomalies should track surface composition, not basin geography. The far side concentration opposite the near side basins is not predicted by the dynamo hypothesis alone. The second is the impact amplified field hypothesis, that large impacts on the near side generated transient magnetic fields through plasma processes during the impact, that those fields propagated through the moon and converged at the antipodal points on the far side, and that the convergent fields magnetize the antipodal surface rocks more strongly than the background field alone would have. The hypothesis explains the antipodal pattern directly. The problem is that it requires the impacts to occur during a period when the dynamo was still active and the magnetization could be preserved, which constrains the chronology tightly and which the data do not yet confirm. The current state of the literature is that both hypotheses are probably partially correct. The moon almost certainly had an ancient dynamo. The Apollo sample evidence is too strong to dismiss, and the antipodal pattern almost certainly reflects impact-related amplification at specific sites. The relative contribution of each mechanism is unresolved, and the resolution requires data the current mission portfolio is beginning to acquire. The data requirement is direct measurement at the anomaly sites, on the surface, with instruments capable of characterizing the magnetic field's vertical structure and the magnetized rock's composition. NASA's Lunar Vertex mission, scheduled for deployment in the late 2020s under the CLPS program, will land at the Reiner Gamma anomaly, which is the most prominent near-side magnetic anomaly and the most accessible target. The mission will deploy a rover with a magnetometer and a spectrometer, and the combined measurements will constrain the anomaly's origin in ways orbital measurements cannot. This mystery is closer to resolution than the TLP mystery. Lunar Vertex will not resolve it completely. A single landing site cannot characterize the full anomaly population, but it will narrow the hypothesis space substantially, and follow-up missions targeting additional anomaly sites are already in the planning stage. The resolution matters beyond the anomalies themselves. If the ancient dynamo was as strong as the Apollo samples suggest, the moon's early interior was generating more energy than the current models comfortably accommodate. The energy had to come from somewhere, from a small, vigorously convecting core, from a thermally driven mantle dynamo, from a precession-driven mechanism powered by Earth's tidal coupling, or from some combination. Each of these implies a different early lunar interior, and the differences propagate forward through the moon's entire thermal history, which raises the question of where the early lunar interior came from in the first place. The dynamo, however it was powered, was operating in a body that had just formed under conditions that the standard model of solar system formation does not naturally produce. The moon is the wrong size, in the wrong orbit, with the wrong composition, to be a body that formed where it sits. The standard explanation is a single event, and the event, on close examination, is the deepest unresolved mystery on this list. The Moon in the consensus model formed when a Mars-sized body called Theia struck the proto-Earth approximately 4.5 billion years ago. The impact ejected a vast quantity of material into orbit around Earth, and the orbiting material coalesced into the Moon over a time scale of years to thousands of years. The model is called the giant impact hypothesis, and it is the consensus explanation for the Moon's existence. The consensus is in trouble. The giant impact hypothesis was developed in the 1970s and refined in the 1980s and 1990s on the basis of dynamical arguments. The arguments were strong. The Moon's orbit, angular momentum, depleted iron content, and depleted volatile content all matched the predictions of a giant impact and matched no other formation scenario. By the late 1990s, the hypothesis was textbook material, and the remaining questions were about specifics: Theia's exact mass, the exact impact angle, the exact post-impact orbital evolution, rather than about the framework. Then the isotopic measurements arrived. Beginning in the early 2000s, high-precision isotopic analysis of Apollo samples and of terrestrial samples produced an unexpected result. The Moon and Earth have nearly identical isotopic compositions across a wide range of elements: oxygen, titanium, chromium, tungsten, silicon, potassium. The compositions match to within the precision of the measurements, which is parts per million for some elements. This should not be the case under the standard giant impact model. The standard model predicts that the Moon should be composed dominantly of Theia, material, because the orbital dynamics deliver Theia's mantle preferentially into the post-impact disk. Theia, having formed elsewhere in the solar system, should have a different isotopic composition from Earth, because the isotopic composition of solar system bodies varies with formation distance from the Sun. The Moon and Earth should be isotopically distinguishable. They are not. This is the lunar isotopic crisis. It is the most substantial open problem in lunar science. The consensus framework for explaining the Moon's existence makes a prediction that the data refutes. Several modified models have been proposed. The Synestia model, developed by Sarah Stewart and Simon Locke in the mid-2000s, proposes that the impact was so energetic that it vaporized a large fraction of both Earth and Theia and produced a transient structure, a synestia, in which the vaporized material was thoroughly mixed before the Moon condensed. The model predicts isotopic homogenization as a natural consequence of the mixing. The model is mathematically tractable and is consistent with the isotopic data. The problem is that it requires an impact energy substantially greater than the standard model assumes, and the higher energy is not strongly favored by the dynamical evidence. The multiple impact model proposes that the Moon formed not from a single giant impact, but from a sequence of smaller impacts, each contributing a moonlet that subsequently merged with the others. The model predicts isotopic homogenization through the averaging of multiple source bodies. The model is consistent with the isotopic data and avoids the high energy requirement of the Synestia model. The problem is that it requires a specific dynamical history that the simulations can produce but cannot strongly favor over the single impact alternative. The high-energy single impact model, a variant of the standard model with impact parameters at the high end of the plausible range, proposes that even a single impact, if energetic enough, could produce sufficient mixing to homogenize the isotopic composition. The model is intermediate between the standard model and the Synestia model and is consistent with the isotopic data under specific impact geometries. The problem is that the geometries are narrowly constrained, and the model lacks the explanatory generality of the alternatives. None of these models is the consensus. The current state of the literature is that the standard single impact model is wrong in its specifics, that one of the modified models is probably correct, and that the data required to distinguish among them is not yet available. The resolution will probably come from continued high-precision isotopic analysis combined with refined dynamical simulations. The simulations are progressing. The computational resources available for impact modeling have increased by approximately 3 orders of magnitude since the original giant impact hypothesis was proposed, and the precision of the isotopic measurements continues to improve. The resolution timescale is, by my assessment, 10 to 20 years. The resolution matters more than any other on this list. The Moon's formation is the anchor for the early solar system's chronology, the composition of the early Earth, and the conditions under which Earth's water and volatiles were delivered. Resolving the formation mystery would adjust our model of Earth's own origin substantially, and the adjustment would propagate forward into our understanding of habitability, of the timing of life's emergence, and of the conditions under which Earth became the planet it became. And it would propagate sideways into a related mystery, because whatever event produced the Moon also produced its most visible feature, the one anyone can see with the naked eye on a clear night. The Moon's two faces are not the same. They have never been the same, and the consensus model does not explain why. The Moon's near side is the face we see from Earth. The Moon's far side is the face we do not see. The two faces should be approximately similar. They are not. The near side is dominated by the Maria, the large, dark volcanic plains that form the familiar pattern of the lunar surface. The Maria cover approximately 31% of the near side surface. They cover approximately 1% of the far side surface. The crustal thickness on the near side averages approximately 60 kilometers. On the far side, it averages approximately 100 kilometers. The far side has more craters at all size ranges, a higher elevation, and a different mineralogical composition. The asymmetry is the largest scale structural feature of the Moon. It is visible in every map. It is the first thing any lunar geologist explains, and its origin is not settled. 4 hypotheses compete in the literature. The first is the differential cooling hypothesis, that the near side facing the hot young Earth cooled more slowly than the far side, and that the slower cooling allowed more extensive volcanic activity on the near side over the subsequent billion years. The hypothesis is physically straightforward and is consistent with the basic asymmetry. The problem is that it predicts a smaller asymmetry than the data show. The temperature difference between the two sides during the relevant cooling era was not large enough to produce a 30-fold difference in Maria coverage. The second is the second impact hypothesis, that the Moon, after its formation, was struck by a smaller body whose impact preferentially modified one hemisphere. The hypothesis explains the asymmetry through a discrete event rather than a continuous process. It has the advantage of producing large effects from small causes. The problem is that the predicted impact signature, a specific basin morphology, a specific ejecta distribution, has not been clearly identified on the lunar surface, and the absence of the signature is a substantive objection. The third is the second Moon hypothesis, that the Moon initially had a smaller companion, that the companion was captured by the Moon's gravity early in lunar history, and that the companion's low-velocity merger with the Moon preferentially thickened one hemisphere's crust. The hypothesis was proposed by Eric Asfog and Martin Utzi in 2011, and is supported by simulations showing that the low velocity merger produces an asymmetry pattern consistent with the observations. The model explains the crustal thickness difference and the elevation difference simultaneously. The problem is that it requires the second moon's existence, which the standard giant impact framework can accommodate but does not predict. And the evidence for the second moon's prior existence is necessarily indirect. The fourth is the deep interior compositional hypothesis, that the asymmetry reflects an asymmetric distribution of heat-producing elements in the lunar mantle, that the asymmetric distribution caused asymmetric volcanic activity over the moon's history, and that the asymmetric volcanic activity produced the maria on the side where the elements were concentrated. The hypothesis has accumulated support from gravity measurements made by the GRAIL mission in 2011 and 2012, which mapped the lunar interior at unprecedented resolution and found a structure called the Procellarum creep terrane, a region on the near side enriched in potassium, rare earth elements, and phosphorus, which together with thorium and uranium are the principal radiogenic heat sources in planetary interiors. The enrichment is real, the spatial coincidence with the maria is precise, and the hypothesis is currently leading in the literature. The deep interior compositional hypothesis is not yet the consensus, because it has its own open questions. The question of why the heat-producing elements concentrated on the near side rather than distributing uniformly is not answered. The candidate answers initial mantle convection patterns, post-formation differentiation, influence from the early Earth's gravity, are all plausible and none is established. The resolution approaching development is Chang'e 6. The mission, which returned samples from the far side South Pole Aitken Basin in 2024, delivered the first samples ever recovered from the lunar far side. The samples are currently under analysis, and the analysis is expected to produce, within the next several years, the first direct compositional comparison between near-side and far-side lunar material at the precision required to distinguish the four hypotheses. The resolution timescale with Chang'e 6 in analysis and additional far-side missions in development is approximately 5 to 10 years. The asymmetry mystery is one of the closer to resolution mysteries on this list, and its resolution will be substantial because it bears directly on the giant impact question from Part 3. The four asymmetry hypotheses each imply a different post-formation history, and the post-formation history is the link between the formation event and the moon we see today. The asymmetry, the magnetic anomalies, and the formation event are all surface and crustal mysteries. Phenomena we observe from outside the moon or from samples returned from its outermost layer. The next mystery is the one we have least direct access to. It lies beneath everything we have measured, and what little we know about it does not match what the formation models predict. The moon has a core. The core's basic existence has been known since the Apollo era. The core's basic properties, its size, its composition, its physical state, have been characterized only in outline, and the outline contains substantial gaps. The characterization comes from three data sources. The first is the Apollo seismometers, which operated on the lunar surface from 1969 to 1977 and recorded moonquakes whose propagation through the lunar interior carried information about the interior structure. The second is lunar laser ranging, which has measured the moon's orientation and its response to tidal forces with millimeter precision since 1969 and has constrained the deep interior moment of inertia. The third is the GRAIL gravity mission, which mapped the lunar gravity field at unprecedented resolution in 2011 and 2012 and constrained the density distribution. The combined data established that the Moon has a small core, approximately 350 kilometers in radius, about 20% of the lunar radius, compared to about 55% for Earth. The core is iron-rich. The core has a solid inner region and a fluid outer region, by analogy with Earth, though the boundary between them is not directly observed. The core is surrounded by a partial melt region of the lower mantle, which is one of the more recent discoveries, and which was not part of the standard lunar interior model until the Apollo seismic data were reanalyzed in 2011 by René Weber and colleagues. The mysteries are in the details. The inner core's existence is inferred rather than observed. The Apollo seismometers were not sensitive enough to characterize the core directly, and the inner-outer core distinction is supported by lunar laser ranging data interpreted within a model that assumes the distinction exists. The interpretation is reasonable, but is not the only interpretation, and the inner core's actual existence remains an inference rather than a measurement. The core's composition is not characterized. The core is known to be iron-rich, but the dominant alloying element, sulfur, carbon, oxygen, silicon, is not established. The choice matters because the alloying element controls the core's density, its melting temperature, and its capacity to host the kind of fluid convection that powers a dynamo. The choice also bears on the formation question from Part 3, because the alloying element's identity reflects the conditions under which the core formed, and therefore the impact conditions that produce the Moon. The partial melt region's nature is contested. The region exists. The seismic evidence is consistent across multiple reanalyses, but its physical state, its extent, and its relationship to the core proper are not well characterized. The region might be a permanent feature of the current lunar interior, or it might be a residual feature from an earlier hotter era. The distinction matters for the Moon's current thermal state and for the question of whether the lunar interior is still capable of supporting any meaningful active processes. The resolution requirement is the same instrumentation for all three of these sub-mysteries. A network of seismic stations distributed across the lunar surface, operating for years, recording moonquakes at sensitivities the Apollo era could not approach. The mission concepts exist. NASA's Farside Seismic Suite is in development for deployment in the late 2020s as part of the CLPS program. The Lunar Geophysical Network mission concept, which would deploy multiple stations across the lunar surface, has been studied in detail and is under consideration for the next Planetary Science Decadal Survey. The resolution timescale is, by my assessment, 15 to 25 years. The seismic network is the prerequisite, and deploying a network of the required scale is a project of comparable difficulty to the Apollo program itself. The resolution will not be quick. When it arrives, it will close three of the mysteries on this list simultaneously: the core structure, the early dynamo's power source, and the question of whether the current interior is still active enough to drive the surface phenomena that opened this video. The interior, however inaccessible, is at least in equilibrium with itself. The lunar surface contains regions whose physics is not in equilibrium with anything. Regions whose temperatures are so low and whose conditions are so stable that they have preserved chemistry untouched since before the Earth had life. And those regions hold an answer to a question that bears on Earth's own origin. The Moon's axial tilt is approximately 1.5 degrees. The tilt is small, much smaller than Earth's 23.5 degrees. and the smallness has a consequence. At the lunar poles, in the bottoms of certain craters, the sun never rises. The crater walls block the low-angle sunlight at all times throughout the lunar year, and the crater floors have been in darkness continuously for billions of years. These regions are called permanently shadowed regions, or PSRs. They are among the coldest places in the solar system. Surface temperatures in the deepest PSRs reach approximately 25 Kelvin, colder than the surface of Pluto, colder than most regions of the Kuiper Belt. The cold is a consequence of three conditions: no direct sunlight, no atmosphere to redistribute heat, and limited heat conduction from the surrounding warmer terrain. The cold has a consequence of its own. Any volatile compound, water, methane, ammonia, carbon dioxide, more exotic organics, that reaches a PSR will freeze and will remain frozen indefinitely. The PSRs function as cold traps. They have been functioning as cold traps for approximately 3 billion years, since the lunar axial tilt stabilized to its current value. Whatever volatiles have arrived at the lunar poles in that time, by whatever delivery mechanism, are still there. The volatiles have been detected. The Lunar Crater Observation and Sensing Satellite LCROSS impacted a PSR in the crater Cabeus in 2009 and detected water vapor in the impact plume at concentrations indicating approximately 5.6% water by mass in the impacted regolith. The Lunar Reconnaissance Orbiter, in continuous operation since 2009, has mapped the PSR distribution and characterized their thermal environments. The Sofia Airborne Observatory detected water on sunlit lunar surfaces in 2020, establishing that water is more widely distributed than the PSR framework alone predicts. The Chandrayaan-1 mission detected hydroxyl signatures across the lunar surface in 2008. The basic existence of lunar polar volatiles is settled. The mystery is what the volatiles are made of and where they came from. The conventional framing positions the PSRs as a resource, as the source of water and rocket fuel for future lunar settlement, as the operational target of NASA's Artemis program and of the parallel Chinese lunar program. The framing is reasonable on its operational merits. It is not the framing that matters scientifically. The scientific framing positions the PSRs as an archive. The volatiles accumulated in the PSRs over 3 billion years are a sample of the inner solar system's volatile flux over that period. The isotopic composition of the volatiles records the sources: cometary, asteroidal, solar wind, endogenous lunar, in proportions that the isotopes can distinguish if the samples can be obtained and analyzed. The PSRs contain, in effect, a frozen record of the volatile delivery to the inner solar system from before the time Earth had life through to the present. The record bears directly on Earth's own origin. Earth's water arrived from somewhere. The dominant hypotheses: cometary delivery, asteroidal delivery, endogenous outgassing, some mixture, predict different isotopic signatures, and the predictions are not currently well constrained by terrestrial samples because Earth's water has been thoroughly mixed and processed over the planet's history. The lunar PSRs have not been mixed and have not been processed. They preserve the delivery record at the source. The resolution requires sample return. Orbital instruments can characterize the volatiles at low resolution. Landed instruments can characterize them at higher resolution. Neither can substitute for laboratory analysis of returned samples at the precision required for isotopic source attribution. The mission portfolio for PSR sample return is currently uncertain. NASA's VIPER rover designed to characterize PSR volatiles in situ, was cancelled in mid-2024 for budget reasons, then partially revived through a public-private partnership arrangement whose final form is still being negotiated as of mid-2026. China's Chang'e 7 mission, scheduled for 2026, will deploy a small hopper into a south polar PSR for in situ characterization, and Chang'e 8, scheduled for 2028 or 2029, will conduct the technology demonstration for eventual sample return. The first PSR sample return mission by any space agency is not currently scheduled before the mid-2030s. The resolution timescale is, by my assessment, 10 to 15 years for in situ characterization and 20 to 30 years for the isotopic precision laboratory analysis that the source attribution question requires. The PSRs are accessible to the current mission portfolio in a way that the lunar core is not, but the analysis chain is long and the resolution will arrive on a longer timescale than the operational interest in the PSRs as a resource suggests. The PSRs hold a record of what arrived at the moon over the last 3 billion years. The question for the next section is what the moon itself was doing during that same period. The textbook answer is nothing. The moon, the textbook says, has been geologically dead for 2 billion years. The textbook is being revised. The standard description of the moon characterizes it as geologically dead. The volcanic activity that produced the Maria ended approximately 3 billion years ago. The interior cooled. The crust stabilized. The moon, on the standard description, has been a passive recorder of external events, impacts, solar wind, cosmic ray bombardment, for the entire second half of its history. The standard description is being challenged from 4 directions simultaneously. The first is the Lobat scarps. These are small cliff-like features distributed across the lunar surface, identified in detail by the Lunar Reconnaissance Orbiter camera over the past 15 years. The scarps form when the lunar surface contracts and the crust thrusts over itself. The contraction is a consequence of cooling. As the interior cools, the lunar radius decreases, and the surface accommodates the decrease through faulting. The scarps were initially interpreted as ancient features. The LRO observations established that they are not. The scarps are young. Many are younger than 50 million years. Some are younger than 10 million years. Some are accompanied by boulder displacements and surface disturbances, consistent with seismic activity within the last few million years, and possibly within historical time. The second is the irregular mare patches. These are small features within the lunar Maria, identified by the LRO and characterized by Sarah Braden and colleagues in 2014. The patches have textures consistent with volcanic activity, and the crater counting age estimates place them at less than 100 million years old. The estimates have substantial uncertainty, but the central values are an order of magnitude younger than the conventional end of lunar volcanism, and the patch's existence challenges the conventional chronology directly. The third is the reanalysis of the Apollo seismic data. The Apollo seismometers recorded moonquakes from multiple sources: shallow quakes, deep quakes, thermal quakes, impact-induced quakes. The shallow quakes were initially interpreted as residual seismic activity from the cooling lunar interior. The reanalysis, conducted by Thomas Waters and colleagues in 2019, found that the spatial distribution of the shallow quakes correlates with the lobate scarp distribution at statistical significance, supporting the interpretation that the scarps are tectonically active and that the moon is currently producing seismic events at rates the original interpretation did not recognize. The fourth is the Chang'e 5 dating result. The Chang'e 5 mission returned samples from a lunar mare region in 2020. The samples, analyzed in 2021, yielded an age of approximately 2.0 billion years for the volcanic activity that produced them, about a billion years younger than the conventional end of lunar mare volcanism. The dating extended the lunar volcanic era by approximately a third of its previously assumed duration, and the extension is direct rather than inferential. The combined picture is that the moon is not geologically dead. It is geologically slow. The volcanic activity has not entirely ended. The tectonic activity is continuing. The seismic environment is more active than the standard description allows. The interior is still cooling, still contracting, still producing the events that the lobate scarps record. The resolution requirement is, again, the seismic network described in Part 5. The same instrumentation that would characterize the lunar core would also characterize the current seismic environment at the precision required to settle the question of current geological activity quantitatively. The two mysteries, the core's structure and the surface's current activity, share a resolution pathway, and the pathway's timescale is the same 15 to 25 years. The reframing matters beyond lunar science. The conventional view of the moon as geologically dead was a major piece of evidence for the standard model of small body thermal evolution, the model that predicts how quickly small rocky bodies cool, how long they remain volcanically active, and what their long-term geological fate is. If the moon is not as dead as the model predicted, the model needs revision, and the revision propagates to every other small rocky body whose thermal history we have inferred from lunar analogy. Mercury, Mars, the large asteroids, the icy moons of the outer planets. The moon, in this respect, is not just the body we have studied the most. It is the body whose study has anchored our understanding of every other small body in the solar system. When the lunar framework shifts, the framework for everything else shifts with it. We started with the proposition that the moon is the most studied object in the sky, and that the most studied object should not have unresolved mysteries. The 7 sections have, I hope, made the alternative case, that study reveals mysteries faster than it resolves them, and that the moon, after 4 centuries of telescopic observation and 6 decades of spaceflight, contains more open problems than it did at the beginning of either era. The 7 mysteries are not independent. The transient lunar phenomena bear on the question of whether the lunar interior is still releasing gas, which bears on whether the interior is still active, which bears on the 7th mystery. The magnetic anomalies bear on the question of whether the moon had an early dynamo, which bears on the core's structure and energy budget, which is the 5th mystery. The giant impact bears on the moon's bulk composition and the conditions of its formation, which bears on the asymmetry, which bears on where the volcanic activity concentrated, which bears on the current geological activity. The permanently shadowed regions hold an archive of volatile delivery whose interpretation depends on the moon's overall thermal and chemical history, which is, in turn, the integrated subject of the other 6 mysteries. The mysteries form a network. The network has been the implicit subject of this video. An explicit recognition of the network is the substantive contribution I want to leave you with. The moon is not 7 separate problems. It is one problem with 7 entry points, and each entry point connects to the others through the lunar interior, the formation event, and the 4.5 billion years of thermal and chemical evolution that link the formation to the present. The resolution timescales vary. Some mysteries, the asymmetry, the magnetic anomalies, will probably be substantially resolved within the next decade by missions already in development or in flight. Others, the core, the current geological activity, require the lunar seismic network whose deployment is a project of Apollo-scale ambition and Apollo-scale duration. Others, the giant impact, the volatile delivery archive, require sample analysis and computational work whose timescales are independent of mission deployment and will continue whether or not new missions arrive. The aggregate is that the next 20 years will produce more revision of our understanding of the Moon than the previous 50 have. The mission portfolio is the largest it has been since Apollo. The instrumentation is the most capable it has ever been. The samples returning to laboratories on Earth are the first lunar samples to arrive in nearly half a century, and the next set is already in development. The computational tools available for modeling lunar formation and evolution exceed the tools available to the original giant impact hypothesis proponents by approximately 3 orders of magnitude. The Moon is in a period of substantial revision. The textbook description that most of us learned, the formation by giant impact, the cooling to geological inertness, the dead surface preserving the early solar system unchanged, is being revised on every term simultaneously. The giant impact is not what the standard model described. The cooling did not produce geological inertness. The surface is not dead, and the early solar system is not preserved unchanged. What replaces the textbook description is not yet settled. The 7 mysteries are the 7 places where the replacement is being worked out, and the working out is, by my assessment, the most interesting period in lunar science since the Apollo program itself. Watch the next decade.